And now we have example 3 from class 15, rigid body kinematics, finding velocities using the instantaneous center of rotation. And where did my page go? Well, if you made it this far, there it is right there. Careful with your sketch. That's what I say right here. Oh, by the way, if you made it this far, I have a guitar sitting right here. So you can't see it, but this is a wonderful Van Halen looking guitar. Van Halen. See, I added a little extra thing there. We can play the beginning of every Van Halen song, but I don't know the rest of most of their songs. All right, that was unnecessary. Or maybe it was, because getting cabin fever, losing it, out of your mind. Anything but more dynamics. But let's do some more dynamics. All right, so this is a problem. This is a tricky ICR problem. So you need to be careful with the sketch I've written there. VD, VD, the velocity of D is not in line with AB. There's a note that I wrote to myself. Okay, so what I'm saying there is that it would be really easy to think that the velocity at D right here was going to be in the same line as the velocity of AB. But I've drawn it. We'll see in a second that it's not. So here's what we know. The two 500 millimeter rods are pinned. So these are both apparently 500 millimeters, although they don't both look like the same length to me. But we'll see they probably are. Connected as shown, knowing that B moves to the left, okay, with a constant velocity of 300 millimeters per second, determine at the instant shown the angular velocity of each rod and the velocity at C. Okay. So how we want to approach this is, let's start out with the stuff that we know. So we'll make a careful sketch of the rod AB. So making a careful sketch, taking this, that's my careful sketch. As careful as I can make it right here. And B is going to the left. Right here. Okay, so that's the velocity of B. So A, we can tell, has to go up and down unless the rod is leaving the surface. We can assume they meant that the rod is going to maintain in contact. So if we draw the instantaneous center, we draw lines perpendicular to these two velocities right here. We find the ICR. And based on that, it appears that this is rotating this direction right there, right? So that's going to be the omega AB. So we could tell that the velocity of A is actually upwards, which kind of makes sense after you look at the thing, that if B is going that a ways, A has to start climbing up the wall, right? So this isn't too difficult. We could find the velocity of B is equal to omega. We don't find it. We already know that. And that's going to be RB with respect to ICR right here. And this is RB with respect to ICR right here, whereas this is RA with respect to ICR. Squeeze it in there. So we could find that omega AB is just going to be equal to that velocity of b, or 360 millimeters per second, divided by RCB, which we could tell is going to be the 200 plus 200, aka 400, and therefore equaling to 0.9 radians per second, and that's going to be clockwise. So that's actually the one of the first things. We had to get the other rod as well. Okay, and so by the way, this is the velocity of D right there. So we can find the velocity of D, but be careful. It's going to be perpendicular. Whoops, got to be very careful with this line. Perpendicular to this line right there. Okay, and that is not in line, it turns out, with AB, right? Comes off over to the side ever so slightly. That's the velocity of D. We need to find this dimension right here, which is RD with respect to ICR. So the velocity, that's going to be from our, okay, yes, we can find that because we know this distance and that distance, right? And well, we have our ICR like right up here, right? So the distance that we want is going to be this distance right in there, which is, yes, okay, so it's going to be 150 right there and 200, right? So that's going to be equal to the square root of 200 squared plus 150 squared. So what do we end up with? That ends up being 250. So that might have been a 3, 4, 5 triangle somewhere in there, working out so neatly. Yeah, I'm sure if you multiplied by 50, yeah, that's a 3, 4, 5. Yeah, just with 50 multiplied by it. And so now we could find the velocity of D is just going to be omega AB times R D with respect to ICR. Right, so our 0.9 times our 250. I'm getting a new microphone soon, just so you know, and so it'll make my voice sound much more silky smooth, and maybe that will make this not as painful for you. Here is a tricky problem. I really kind of need the angle of VD right here, and I'll try not to giggle when I say that. So the sketch I've made right there, it's a little too crowded for this, and so I noticed that I did this for myself previously. Let's see if I can repeat the thing again. So what I did is I carefully made a larger graph right in here of this piece, and here I went with, this is my 150. I said 150 and I wrote 120. I wrote 150 right here, and this is 200. Right now, I'm going to come over another 50. Right, so that's going to be over to there. I'm going to come up. Oh, yeah, that wasn't great. Right in there, and that right there was, and that, by the way, is supposed to be this should be symmetric about this right here, right in there. This is my point D right in here, and if I'm going to get if I want to get the angle, I decide to get this angle right here. This is of beta here. So I have beta is equal to the inverse tangent of the rise over the run. So that should be 200 divided by 150, right? It gives me 53.13 degrees. And where are you at? Down here. Come on. This thing's mad at me. There you go. Let's see. We'll draw up here as best we can our angle right there. There's our velocity at D right in here. And if we're looking at this, we would find that we also have this angle is going to be the beta right in there. That angle that's formed right in here. That's beta. So what we really want to be able to do, come on. All right, I'll just use green. We want that angle right there, which is going to be 90 minus 53.13, or a very common one to see, 36.87. We relate that to, we see that often with the 3, 4, 5 triangle. Okay, so we could switch over and let's go to red. Why not? Now when I come and do my diagram for my, come on, give it to me. There you go. Whoops. Why are you doing this? Come back. All right. I think the machine is slow. Now we want to do the, for our other bar. We'll do a diagram for our other bar. Let me see. Am I going to get in the way? Okay, so I need some space for this one. Well, let me get his geometry a little bit better. All right, so there you go. The velocity I want to apply to this is like right here. Noting that this right here is our 36.87 degrees right there. So that's the velocity of D. All right. And I know that my velocity of E needs to be along this line right here. So if I'm going to find an ICR, it needs to be along a line that's like right in there, right? And in order to do that, I need a, whoops, what happened here? We are in a great mood today, yeah. This is where the ICR is going to be located for this. This is the ICR for this. Yeah, it is a fun one, right? Oh boy, great. And now if you want the angular velocity of this is going to be found from right here. So that's going to be the dE. And that also lets us know that the velocity right here, velocity of E, is going to be to the left. We might not have been able to tell that from the original position, but now using through the ICR, we're able to convince ourselves that that is the direction that the thing has to rotate. What we need to find to be able to find this omega right here, because we know the velocity D, we need to find the D with respect to that ICR. We need this distance right in there. And then if we want the velocity E, we also need to find this distance E with respect to ICR. So that is now our geometry challenge. not necessarily something that's going to be a lot of fun. But we just walk through the thing. Now, one thing that we do know about these distances right here is that we are given this 150 plus 250 is 400 and 400, yes. And we know that this distance is 200 and this distance is 500. Therefore, this distance right here is going to be 300. And based on that right here, we also can tell from that right triangle right here that we know that this is 90, so that this guy right here has to be that 53.13. And from this being a right triangle, we're able to also see that, okay, so that up here as being a, yeah, okay, so I should not have gone around into this upper corner by the E. I need to be up here, right here. So this guy right here. So this is also going to be the 36.87 degrees. So that doesn't make it too bad. So if we want to get the distance, this, let's switch colors here. Come on. There you go. Switch it to, we had used a purple already. We used a lot of green. Let's go to this dark red. Okay. If we want to find, I'm looking at this. Where'd you go? Oh, I see what I did. I took the sine of that angle right here and 400. Okay, so I could actually do this in a number of different ways. Let me just follow the way that I did this right here. I took 400 is equal to RD with respect to ICR, right? So I'm going that guy right here times the sine 36.87, although there was a bunch of other different ways I could have got that. So RD ICR, that length, the hypotenuse of the thing is the scary 66. Whoop. I could jump the gun with the decimal place right there. A little Iron Maiden action. 666.6. That makes it better. What did I say? Millimeters? Yes, millimeters. Millimeters. From that, we're able to get that omega DE is going to be VD divided by RD ICR, or so it's going to be 225 divided by 6. Keep adding a decimal place in there quickly. 666.6, and so we end up with 0.3375 radians per second, and that is clockwise, as we found up here, right? That was clockwise. And so that actually answers the second part of part A. And then for part D, we're going to need to find, I'll go over here in the left right-hand corner to find VE. We need to find we use the omega DE we just found and multiply it by the RE with respect to ICR. So we need to find that, and the way I went about doing that, I guess I just wrote the thing out. Okay, I said that R E with respect to ICR is this length right here, right? It's going to be that entire length. And what did I do? I took equal to 400, because I knew this right here, divided by the tangent of our 36.87 0.87, and then I subtracted out the 300. And I found that it was equal to 233.3 millimeters. And so I was able to find VE is equal to our 0.3375 times our 233.3. And we end up with 78.75 millimeters per second. So, and we did ask for velocity, so we really should answer with our 78.8 millimeters per second and with an arrow. Boom. So that's part B of the thing, and part A is partially here and partially right here. We really should write that out again. So that's a problem example, example 3. This is a trickier problem, more difficult. Hopefully you followed the idea behind it. Once again, you probably could have do a better job than I, or find other schemes to find the geometry that you need to. You need to try to practice that. That's the only way that you get better at it. So thank you very much, and stay healthy, everybody. And we should add more guitar here at the end. Right? You should waste your time because you went this far right here. Let's hear something off of 1984. This is...